Okay, shall we get started? We're going to learn yet another new algorithm for dealing with graphic models. And it's very different from what we talked about before. It actually has a close connection to the fundamental linear algebraic technique. This technology is known as spectral learning. It was a very hot topic about 5 years ago, which actually really offered a new way, again, to look at graphic models from a new angle so that new algorithms and combinations with other techniques were enabled, just like we saw in the previous lecture, where the regularized Bayes method enables also some new opportunities. These days, I would say it's not as hot or active as the past few years. I guess everything is not as active because of the dominating influence of deep learning. But I think after a while, after all the hot trends are settled and find their sweet spots, it's necessary and in fact very useful to revisit many of these ideas and see whether there are new opportunities for them. Okay, so what is spectral learning approach? It has something to do with latent variable models. As you may recall, one of the major advantage of working on probabilistic graphic model is that you can bring in latent structures which allow a lot of domain knowledge to be introduced into the problem and the model. And also it provides vehicles to do sometimes good and effective influence. And also it has nice characteristics such as interpretability, that you can interpret the meaning of latent variables so that you can explain the outcome. So here are some examples, right? So your sequential models, your observations are basically this, but you can introduce the latent states as we did in HMM and in common filter, where the latent variables may be an intermediate form or maybe a unobserved fact that is dictating the observation, and then you can introduce dynamics such as first order or higher order Markovian properties. And in natural language processing, if you pass a sentence, obviously the pass structure is a latent tree, and by incorporating this, you are able to really encode linguistic syntactic knowledge, and then also to drive inference algorithms. Latent space models, you saw topic models already, and here I have a model called the mixed membership model. Again, it's about embedding complex data into some latent space where things can deconvolve or can be visualized more easily. And in this case, it's the embedding of a social network in a 5-dimensional latent space where you can see nodes projected into the space, and the size correspond to their degrees and so forth. That allows you to visualize nice clustering effects. So here are some other examples of latent variable models in natural language processing, which we used to validate some of our approach in the past. There's a cost for latent variables because they are latent. Therefore, when you train the model, you cannot rely only on the observed data. You have to impute the latent states so that the maximum likelihood learning can still carry forward, right? And that's why we use a EM algorithm so that you can impute. It's an iterative approach where you can impute the latent variables based on a posterior of the latent variable given the observation, so that the whole model become now all observed. Then you can use a maximum likelihood estimator to update the parameters, then you re-estimate the latent variables and iterate until convergence. And we knew actually it is a very intuitive algorithm. Statistically, it also has a good property, but there are some computational difficulties. For example, it's iterative, therefore, the convergence can be slow. And also, latent variables are not optimizing a convex loss function. The likelihood function has a lot of values and non-convexity. Therefore, you have local minima problem, so that you need to randomly restart the algorithm multiple times. These are heuristics to overcome that. Now, spectral learning algorithm was favored by many researchers because it exactly address some of the problems I just mentioned. The idea is to reverse the trend, to remove latent variables so that you avoid some of these properties, such as latent variable problems, such as local minima problems, slowness of convergence, and so forth, and still provide a strong theoretical guarantee of correctness. Now, it seems to be a little bit paradoxical that on the one hand, we want to use graphical models to, introduce latent structures, but there's no free lunch in this world. You have to pay a cost. And now here, this technology is to reverse that, so that you ignore latent variables. So you may ask, okay, then why we even go to the detour of latent variables at all? We can just directly model data, such as we did in regression or that, right? Okay, so here I would argue that the graphic model insight are still useful because spectral algorithms is using the latent variable models, such as HMM, as a guide to allow factorization based on observation, as you will see later, so that you don't actually use those latent structures for computing, but they are intellectually guiding you to break down the bigger computing into smaller problems. So it is actually influence the calculation in an indirect way. Here are some relevant references. You are welcome to take a look when you have an interest into that. So now, just go back to the very basic problem. Why, after all, latent variables can be ignored in some cases. In fact, sometimes if your goal is to use the latent variables directly, such as a visualization of the projection, or like in the supervised LDA we talked about last time, your latent variable is the input of a predictive function. Well, maybe you want to, after all, see that. But in many cases, such as many of the linguistic applications, your latent variable is an intermediate kind of vehicle to make future predictions of the observations. It's like your past is this, and you want to predict what is going to happen in the next time point, and you are using the latent states to bridge them, right? So that you can introduce Markovian properties, and you can use a latent state, such as, I'm modeling the casino guy picking the dice and all that, right? So that's basically why latent variable can appear to be very useful. But if your goal is to really just focus on prediction, and at the end of the day, these guys are not something you actually care about, you may ask, intellectually at least, do I really need to compute all this? Maybe or maybe not. If I'm not so curious, if I don't care about the interpretability, I just want to care, a precise outcome and also efficient computation, there may be a way to neglect your work, neglect the inference work on this part. So that's basically what the spectrum algorithm is taking advantage of. Okay. So maybe you can ask, okay, if I don't care about the latent variables, statistically, I do have a way to remove that, right? So you can do marginalization. What does marginalization effectively leads to? If you have a latent variable model and you sum them over. Well, it leads to effectively a clique model of the observations. Do you actually get that point? Once you remove all the latent variables, you can have no way to factorize the joint distribution of these observations. Therefore, they become all interdependent. That's effectively a clique model of the whole thing. Okay, just like this, you can see that you cannot factorize this. And that means the joint distribution is necessarily a gigantic table of all possible outcomes. That's the extreme of the potential of a joint distribution of the random variable. All complexity, all possibilities of combinations has to be taken care of. That's basically why you don't want to do marginalization, because the latent variable allows you to factor the distribution in an intuitive way so that you can reduce the computation. Okay, so then you may ask, exactly, what the difference between a HMM and a clique model if we just focus on the observation. HMM with observation with marginalization leads to something like a clique algebraically, but are they really the same as a full clique model that I just began with by writing down all the hidden states, all the observations? Okay, so let's consider the following model. Actually, I want to claim that, first of all, they are different. Okay, even a marginalized HMM model can be different from a clique model, at the core, even though symbolically they all are becoming unfactorizable. So now let's get down to a little bit more detail. What is the difference? Let's consider even a simpler model, okay? Just a 3-node model with 1 hidden variables. Okay, so this is a hidden states. In fact, depending on, if we only worry about this, the marginal of the observations, I would claim that depending on the number of states allowed in here, what you can achieve in here can correspond to very different, models of the 3 random variables. Okay, so this is kind of mysterious, but let's make an example. Let's imagine that H has only 1 state, maybe of only 1 element. And do you know what's going to happen to this joint distribution? Yeah. The truth is that if you have only 1 state, then this model is equivalent to this model. You know why, right? Because that means, regardless of the value of the H, you are going to have the same thing for this joint distribution of the 3. Okay, therefore, you just multiply them 1 by 1. They are not influenced by H. The other extreme is, so if you don't believe that they are completely independent, if you believe they are somewhat dependent or fully dependent, of course, means that you have a clique. And they could also have such as this, such as other ways of. Does it have something to do with the cardinality of H? Okay. So maybe what you can, let's visit the other extreme. For example, suppose each of the X has M states, and my H happen to have M to the cube number of states. Then what does this model correspond to? We just said that if it has equals to 1 state, then we got this fully factored thing. If it has M to the power of 3 states, what does the joint distribution correspond to? Have a guess? Conditioning on H, and the H has M to the power of 3 states. meaning that for every possible outcome of this, they correspond to one possible H. Therefore, all different combinations of outcome is captured. Therefore, they correspond to a clique. It's equivalent to a clique, right? So that's the other extreme. Now you can guess that what if my H is between 1 and M3? Well, the extrapolation is that it must be somewhere in the middle, right? It's either something like this, or it could be something that is even softer, that is not described by a graph, right? They may have a weaker dependencies that is not obvious. I don't know, but at least it has to be something in the middle, right? So that's pretty much the point. You can have a view based on linear algebra that allows you to count basically the number of hidden states, so that the dependencies of a fully observed model of random variables in a fully observed model can be captured as if there are latent variables in a full graphical model. Okay. Let me repeat. So what we are going to do in spectral learning is that we will be only focusing on this, okay, P of x1, x2, x3. But we are going to find out a way of their factorization using a linear algebraic property, so that we capture the situations in here, which really amounts to the rank properties of all these different building blocks, which helps you to achieve the effect of a hidden random variable models. Okay, so that's a high-level statement. Let's see how it happens. We are going to use a few notational shorthands to describe certain operations I want you to remember. One is called a sum rule, which corresponds to the marginalization, okay, of a random variable of a joint distribution out of a factored form, okay, x conditioning on y times p of y and the sum over y. And algebraically, this corresponds to a dot product between a matrix, which is the conditional, and a vector, which is the marginal of a singleton. Pretty obvious, right? And that leads to also a vector of the remaining random variable. So this is a particular operation called the sum, okay? And here I have example. And the other one is to produce, a joint from two components. One could be a conditional, the other could be a marginal, and this is a matrix, and this is a vector, and this is what? Also a matrix. So how can you manipulate the algebraic product multiplication where a matrix times a vector becomes a matrix again? Well, that doesn't exist in linear algebra, right? So you need to twist it a little bit. You are going to turn this into a diagonalized form of the matrix. Okay, then it becomes matrix times matrix. And that's basically getting you back a matrix of, the joint. Avoids, the summation caused by the collapsing of the dot product. Okay? All right, so chain rule and the sum rule are the two major operations we are going to use, and let's see how to create a linear algebraic view of the graphical models. Again, start from two random variables, and let's say two random variables A and B each have m states, and it is a full matrix, okay, if we have no assumption. And you can really not say anything about the nature of this matrix if you take no assumptions. But let's see. What if we assume that A and B are independent of each other? Suppose that we have a thing like this. A and B has no edge. This is a new graphical model. And you can write down A and B as a joint as well. And how does this matrix behave? compared to the matrix under no assumption of A and B. Auto product of two vectors, and well, that's when you. But the resultant matrix has what property? Yeah, it's a rank 1 matrix, right? So basically, if I give you two matrices, I'll give you one matrix, okay, and you can always compute the rank of that, and you'll find it's not full rank. In fact, it's rank 1. You pretty much can determine that it is independent on the column and the row dimensions. Okay. Okay, so that's a good a nice connection, at least between the graphical model topology and the linear algebraic properties of the joint. Okay. And what about something in the middle? Okay, we have the full rank, we have the rank 1. What about other ranks that is in the middle? Say, rank, say this. We have a graphic model with a latent variable which causes A and B to be conditionally independent. And I'm going to make this claim. Okay, suppose that my X has a K states. Okay, then I would claim that the rank of A and B is always going to be upper bounded by K. Okay, so that's another connection, between the graphical model and the matrix property. Sorry, I should go backward like this, right? So here we have two graphic models with no hidden variable, and here I have the third graphic model with a hidden variable. Then I say that the cardinality of the hidden variable connects directly also to the rank properties of the marginal probability matrix. Okay, and you can prove it. Here is how you prove it. Okay, you can basically now just using the chain rule I just described to decompose the marginal probability matrix into the product of these three things. Okay, and if this is rank K, then obviously this is going to be rank K, and this is going to be rank K. Therefore, this one will be. Okay. All right. So that's basically getting you to the so-called spectrum view of the graphic models. You are going to purely rely on linear algebraic properties of the matrix, which correspond to a joint. In fact, later will correspond to something else. To draw connections to the effects achieved by latent variable models in graphic models. Okay, so let's take a more interesting example so that you can appreciate it even more directly. We have now a HMM. Okay, and the hidden states are two states, K states, and the observations has M states. Let's assume for now M is greater than K. Okay, and for example, here are two dices, and here are 6 faces, like that. Okay, and you can write down now the joint of say 4 observations, which gives you this big matrix. And we know that it has rank K because of the previous argument. Now I'm going to ask you to factorize this distribution so that they can produce from smaller distributions. How to factorize it? And well, this is the standard way of having a low rank factorization, right? You are going to, turn them into a outer product of two rectangular matrix. That's one way to factorize it. You can compare anything. You remember we have this truth table that your 6 states could give you combinations of 6 variables, and we can put them all to the rows, and you have one column in the number, which is the probability. right? So here is the, x1 and x2 jointly take some configuration, x2 and x3 and x4 take some configuration, and then the entry here tells you this probability. Yeah. And you can show that, by, in fact, the same argument I used in here, because it can be produced by products of smaller matrices. Okay. In fact, I'm going to show you one of these products already. That's the so-called the obvious factorization, where you just introduce a pivot, okay, so that you can define, the 1, 2, and the 3, 4 to be independent given the H2. And then, you obviously can see that the latent variable, if it is K here, then everything else has rank K, right? Okay, so this is a factorization which is probabilistically totally, legitimate and natural, right? Hidden variable H, it's roughly correspond to something like this, right? And why this is possible? Well, it's very easy. You pretty much can just group this into a super variable, hidden variable, and then all the others connect, right? So hidden variable is an abstract thing that you can place anywhere, including in this way, but also in other ways, to introduce some kind of lower complexity dependencies. Okay, so this is a one way of factorizing, which allows you to really prove the rank properties. And also, it gets you a way to simplify the joint. Right? Remember, one of the major achievements in Clique model is allow you to factorize a bigger one into multiplications of smaller ones. And in here, we achieved a little bit that by introducing one random variable h, we are going to now make this table a 3-factor table, and this one a 3-factor table, and this one a 1-factor table, although on the left-hand side we have a 4-factor thing. If you use the full HMM structure, then you can even factor further, right, by having 2-factor tables, element building blocks. All right, but here my point is not about all different ways of further factorizing the hidden variables so that you can get smaller and smaller building blocks. I'm going to pursue a different angle to factorize it, because here the factorization seems to suggest that you need to pivot it with a hidden random variable, right? And that means that you need to learn the hidden variable. If, for example, if you want to train this table, how do you train it? An EM algorithm, right? Magically, I will tell you that there exist factorizations which contain no hidden variables, so that when you train that model, you don't need to do EM algorithm at all. Okay, so here let's take an example. First of all, we know that there isn't a unique factorization, and let's consider the following thing. First of all, the non-uniqueness is pretty obvious, because for any LR factorization of a matrix, you can always insert a invertible transformation in the middle, so that you can basically group these and group these, they become a different transformation, right? So that's basically the non-uniqueness. And then I claim that by choosing this S implicitly or explicitly in a peculiar way, you get rid of the hidden random variables. And here is how we achieve that. Okay, kind of tricky, but it's very interesting. We first set up our goal. Okay, we started from a joint of 4 observed random variable, and we know that this is an expansive distribution which really allows no assumption to be included, such as dependencies, which connects to the low rankedness, right? So let's set a goal that we want it to be break down into smaller matrix. Let's say these 2, which contain only 3 random variables rather than 4. At least you achieve 1 degree of smaller complexity. Okay, how to achieve that? Let's look at this one first. By introducing a pivot, which we call H2, we could rewrite this into a product of these three things, right? So we know that. And do the same for the next three random variables. We can also achieve a product where the H, pivot, H2 away from X3 and 4, okay? Okay, now let's take a little bit a closer look of this. Look at these three things, these three green stuff. Okay, I should really maybe use a different color. This guy, and this guy, and this guy. When they multiply, what do you get? Right? Okay. And then imagine that we have also these three terms. When these three terms multiply, what do you get? Okay. Now let's multiply the two equations together. On here, you have two terms with three variables. And on here, you have two terms, one with four variables, and the other has two variables, right? So what you get is something like this. You are able to now decompose this four-variable joint distribution into a product of these three terms. Okay, each of them basically correspond to a much smaller, at least obviously lower rank matrix. Okay, because you have three random variables here, 3 and 2 here. Okay. So this is a alternative factorization. It means what? It means that to learn this joint distribution, what you need to learn are basically these three tables. Okay. Each of them only requires you to count a much smaller matrix. Not much smaller, one variable fewer matrix. Okay. And there is no hidden random variable. Therefore, you don't need to have a EM algorithm. What do you need to learn basically is literally just to count the triplets or the couples and then fill them into a table. Then you do this multiplication, you get the joint probability of the bigger set of random variables. Okay. And of course, the caveat, of course, is that not all the building blocks are now a probabilistic table. For example, this one is not a probabilistic table. It's the inverse of that, right? It may have negative numbers, but we don't care. If your goal is to make a prediction of some parts of the random variable in the observed space, then all you need is just plug in the numbers. So this is called the observable factorization, which is really giving you advantage of training them without using an EM algorithm. And graphically, again, it captures essentially the same properties as HMM without using all these hidden random variables. Basically, what you did is you introduce a pivot in H in here, and then you are going to now, worry about this triplet, and that triplet, and this pair. And as I said, the observed factorization is not unique. Therefore, you can even explore yet another factorization. For example, you don't have to count 1, 2, 3 together. You can count 1, 2, 4 together. Okay, and using this as a pivot and pivot in a different way, and you can still train the models. Okay, and you may wonder how does it relate to the original factorization here? Well, there is a way to relate it if you really are curious, right? So originally, you have this factorization. I'm using a hidden random variable. You can still turn them into a LR factorization by grouping the first two together and the last one remaining. And therefore, each of them contains a factor of 3 things, although there are hidden variables. And what we just made, as I claimed earlier, is to find the right S, the invertible transformations in the middle to basically kind of fold out the hidden variables. So what this S look like? Well, in fact, if you knew ahead of time that you choose S to be this, okay, actually it achieves you that the same factorization as before. For example, these two correspond to the previous L here times this S, and the remaining one correspond to the S inverse times the R. Okay, so this is just to clarify the correspondence, of how to rotate the matrix to kind of rotate out the hidden variables and only allow, the observed table, observed characters. Yeah.
Sort of an alternative question. For here, you're assuming that the random variables are discrete.
Yeah, I'm going to talk about it continuous later. Okay. Yeah, there are ways to it. Yeah, in fact, that's a very good question. The literature of graphic models always began from the discrete random variables to allow, message passing and other things. But in fact, going to continuous is going to be very easy in this case. I'm going to, so that I need to only save 3 minutes to cover that at the end of the lecture. Okay. All right. Let's see what else. Oh yeah, you may wonder, no big deal. After all, I turned the variable of the joint probability of 4 random variables into a product of terms with 3 random variables. I didn't save much. But the point that this is a chain reaction that you can apply to a longer chain, right? So number 5 random variables. You can basically introduce a pivot to basically turn them into components of 3 factors and 4 factors. And then these 4 factors can reuse that trick we did before and then turn them further into product of 3s, right? So at the end of the day, you can basically achieve a bigger breakage of this into smaller factors. This is recurrent. Training. Did I have? Okay, I think. Before I go to the consistency argument, and I want to make sure that you don't just assume the trick I applied earlier only works on chains. Other graph models, such as a tree, can use the same technique. Okay. If you want to find out the details, you can go to a paper that we are going to post, where a conditional latent tree model, with multiple random variables, can also be factorized in this way into product of little things, to capture the tree structure, and then the training amounts to learning all these triplets of observed random variables. Okay. So I want to claim a few good properties of that in training and testing, right? So in the training, all you need to do is to really compute all these sufficient statistic and get a maximum likelihood estimation. And if, for example, the inverse exists, we're going to talk a little bit about the existence of the inverse, then all these are, of course, consistent, right? They are just a very trivial maximum likelihood estimation, and there are no local minima problems because all you do is to count the observation, the frequencies of states in the observation. And in the test, you are going to basically just plug in your observations, that you want to make a prediction on, into this big table, and then get a number out of it. So it's pretty straightforward. And consistency, as I said, is natural. Okay, so that's pretty much the basic story about the spectrum graphic model. Let's look into the details to see a few catch that I kind of glossed over. So the scenario where this latent states translates to rank of the matrix really enters when we start introducing, first of all, pivot random variables, and as a result, leading to factorizations over observed matrices, which are not necessarily a probabilistic table, right? So here, for example, we have this. But at the end of the day, they need to still go back to a probabilistic table, right? Therefore, obviously, these are not arbitrary matrices that you can learn from, right? And for these two, these are pretty natural because they are joint probabilities. You actually, when you are learning them, you already know whether they're legitimate or not. You actually, already have a partial consistency, at least on this part. This one is going to take you some faith. You are learning a matrix of a joint probability of a subset of random variables, but then you're going to invert it so that a bigger joint can be deduced out of it, right? So here the assumption is already that this must be invertible. But what if it is not? Right? It is not necessarily always invertible. So that actually goes to some additional needs of treating a matrix like this. For example, we knew that when this can be uninvertible, for example, do you actually have a good sense? It's not full rank deficient, for example, right? Then it's not invertible. Then you cannot basically do all this manipulation. So let's look at a few tricks to invert an uninvertible matrix. In one of the cases where, say, M, remember, is the number of hidden states, right? And then I have a hidden variable which is having fewer states than that, which is pretty natural in our latent variable problems. Then what you can do is that you can actually introduce some transformation node matrix, which can be the singular value of the original matrix, and then you can kind of expand, the dimension of this matrix, to basically promote its rank into comparable to D. Okay, so that's just a pure algebraic treatment, which allows you to still manipulate in a lower rank, smaller joint, but working with higher rank, more observations to form a joint distribution. The other scenario is opposite. When you have the K greater than M, this is the situation. Let's say this H correspond to more states than the observations. It turns out that in these cases, the corresponding inverse of 2 and 3 will be harder to deal with. Because this, without having the hidden states, these two cannot basically get a expansion of their dimensionality. First of all, let's maybe take a look about why this actually happens, so that we can hopefully find a remedy of that. Can you imagine why I have more hidden states than observations? Kind of peculiar, right? So that actually corresponds to what is known as a Lagrange effect. For example, giving you this very example, suppose we have this generative process that with a probability of a half, your states, your observation can pick, X and Y, and then you can also print the A, n times, and then you can print S and so forth. So in a sense, your observation will be only having, say, 3 characters, right? But imagine you introduce a hidden states to do proper generation of this sequence. You have to also, the H has to actually remember how many states. Well, this many states, because you need to remember the number of copies that A needs to be printed, right? So out of 3 observations, the sequence needs this many hidden states to capture. That actually causes the latent states to have a greater number of observations, right? So how to deal with this in the spectrum framework, where you have a latent variable that has a higher rank? So in that case, what you need to do is to really introduce something, not just giving you the factor of components of marginals like this, which counts literally the 3 random variables. What you need to do effectively is to really make the factorization to count more information rather than just the 3 observations in here. For example, you can cover something like this, okay, which really allows you to take into the long range effect directly into observation. We're talking about the long range effect, but in the traditional HMM factorization, we're not counting the long range information, right? And that actually causes your rank deficiency. You just don't have enough complexity. But once you do this, to have a longer feature information so that your table becomes a higher rank, then you can accommodate a higher rank latent variable, and then also the higher rank information in the pivot. Okay. And here already gives you a hint already where the continuous random variable are going to be introduced. Because here we're really talking about a mapping of the observation to some features, right? It's a feature vector, and in there, it could be just the discrete states configuration. It could also be something else, as long as it is a table that can be transformed in some way into a probability, in your operational space. So this is basically going to a new dimension that is very interesting in spectral learning. That is spectral learning with features. We began from working with this discrete table, where the way to form this, we say it's by counting, but it is actually by a outer product manipulation of 2 feature vectors, which are the count vectors, right? And you can just extrapolate the idea into the expectation of not the count vector, but the feature vectors, okay? And then still working with this table, which gives you, that kind of, more flexible properties. So this joint will be now, composed by, this matrix, and that matrix, and that one, which can have higher dimensions, and also flexible numbers of the features. Okay. So up to here, we really are wrapping up, the manipulation and the basic foundations of spectral learning. So the catch is that you are able to you are able to perform a so-called observational factorization, okay, of a joint distribution, which is giving you the same power in terms of modeling the marginal, okay, over latent verb models such as HMM and trees. Although they are not equivalent because you lose the capability to model latent variables. But in terms of the dependency, the richness of the marginal under observation, this type of latent spectrum technique gives you roughly the same power. They may not have an exact one-to-one correspondence, but it's very close. Okay, yeah.
So just to clarify, if your modeling assumption is wrong and k is larger than you thought it was, and you try to run the algorithm, does it give you like error, like range efficient matrix?
Good question. If your assumption is wrong, usually your model will work with your assumption. If you are only willing to say, you count the short range effect, say these 3 states, you're not going to get error message. Okay. You're still going to push the work, but your model richness is weaker. Right? Remember that the hidden verb model makes everything very explicit. You knew that I want to design higher number of states in the hidden things so that I can do long range things. Right? So it's a model design. If you do short thing, it wouldn't generate error. It's just like you cannot make good predictions.
So in practice, the matrices never are range efficient?
In practice, I think the other side of the problem, it's probably your k is smaller than the m.
Oh, so you said, got it. Okay.
Yeah.
So you have,
that part will give you error message, but then you can correct it very easily by pedaling them on the left and the right matrix to boost up the whole thing. Yeah. But when your k is in your modeling world bigger, you cannot achieve that without a design because in your 3-factor, 2-factor, and 3-factor, defactorization, your k can only be as big as m, right? And that's where you need to put additional design to count longer range. Yeah. Other questions? Again, so the point is that these kind of technique are not very, very often seen in modern, deep learning type of work, because in fact people don't bother spending time deriving all this. It's kind of complicated. It requires you a careful knowledge into the model to meticulously kind of break them down into pieces. And if I give you a 200-layer deep neural network, and with convolutions and pooling and everything, what you expect is the TensorFlow kind of effect. You have an automatic engine just does everything for you. You don't need to worry about that. But there's no free range. You lose this kind of intricate, very sophisticated knowledge, right? And I believe that's one of the reasons why these models are not practiced, but also means that there are a lot of opportunities because if you care to try or embed some of this technique into those fancier, bigger models, I don't know. There may be some surprising good outcome out of it. Okay, and in domains where it actually was practiced was like latent tree models and HMM, which are very regular, very structured, and people did spend time work it out. It turns out that they get better parsing results, better the predictive results. Yeah, and they are particularly useful when you don't have enough data. Okay, usually for data, big neural network require a lot of model to train. Otherwise, you really cannot get too many things out of it. But for smaller data, how do you still maintain stability and the consistency of the training results? This kind of technique, which really takes less assumption and less demanding on the algorithm, will give you more stable results. So here are some experiments just to give you a kind of idea about how it compares to other models. And by the way, here are applications to both synthetic and also real data. In synthetic data, you can always try different orders of dependencies, different tree structure than that, and you have ground truths. Therefore, you can compare the accuracy. And you can see typically, if you are talking about the runtime, this algorithm is extremely efficient, right? Because you don't. It's a one-pass algorithm. You don't really need to do iterative kind of calculation. The costs are mainly about inverting that matrix. That's it, right? So it's not a big deal, especially when you have a good structure that allows you to do effective factorization. EM algorithms, you can see that their costs go up very, very quickly with the training samples. And in terms of data dependency on the model quality, Spectral has a nice property. It's very, very stable, and there is no surprise. Obviously, the error goes down when you have more and more data. And for EM algorithm, it depends. This is called an online EM algorithm, which is a twist where you are not swiping the whole data every time. When you get more data, you incrementally train it. It's like a stochastic gradient type of style. And it's comparable, to the Spectral algorithm. Okay, but if you have an offline standard EM algorithm, you can see that when the data goes very big, it doesn't actually improve model very much. It's not very data efficient. Why? Because if you are given a huge data set, that means the latent space becomes very, very complex, more irregular and less smooth and convex. Therefore, you are more difficult to jump out of local minimum as a result. But the stochastic versions of that gives you a little bit better, but they are no better than the Spectral, because Spectral even bypass that problem once for all, right? And they are computationally more efficient. It doesn't mean Spectral algorithm is always the ideal thing, because it really requires you to work with the model carefully to do the decomposition. That's not automatic. It's by design. On the supervised parsing, the results are, I would say, are pretty encouraging. If you can see that there is a comparison of the numbers, and the EM algorithm, the Spectral algorithm usually, become better, when you have a higher number of hidden states, which makes the problem more complex. Then, this column of solutions are more competitive. And of course, training time is always an advantage, right? It's really orders of magnitude, faster in certain problems. Okay, so now let's spend the last few minutes talking about a few other things. It's sometimes difficult to run this kind of EM algorithm if your distributions do not fit into a parametric family, right? Basically, if you have a continuous random variable, what do you do? Even in the traditional graphic model thing. Well, we kind of feel that graphic model can handle continuous random variable, but in the parametric world, you don't have too much options. Usually, you want to assume they are Gaussian, right? So in the HMM, you can have a conditional Gaussian of every state, and then you appear to be able to do continuous variable or time series modeling. But we know that many of the data are not Gaussian. And they may be a mixture of Gaussian, or they may be even more irregular. So in that case, using I wouldn't say it's the fault of the EM. It's the fault of probabilistic graphical models, which really depends on very, very explicit design of conditional distributions to be somewhat limiting, because you have to be able to express them in a parametric way, right? And the modern days, you have now Dirichlet process and Indian buffet process and Gaussian processes, which makes you a little bit better. Well, I wouldn't say a little bit better. They give you substantial more modeling power, but they are very, how should I say, data-driven. It's an expensive algorithm. Especially in Gaussian processes, you will see from next lecture that every single prediction is in principle dependent on all past data set. Therefore, you need to keep that, non-parametrically, which is expensive. Dirichlet process is a little better because it's after all a class stream model. So you can do something called the semi-parametric technique, that the data can be summarized into clusters. But clustering problem is just a subset of many of our problems. When you do prediction, it's less powerful. So now let's see how can we take advantage of the Spectral technique to hopefully allow us more flexibility in here. So here is the idea. Again, going from the very definition of the joint probability. This is equivalent. You can always define the joint probability to be the expectation under a certain distribution of the outer product of two indicator vector, right? And the indicator vector, as I said, is a form of the feature vector. It's basically a discrete feature vector where everything else is 0 and 1 is 1, right? And we can always try to replace them with a more complex feature, okay? And the complex feature can be local or can be global, okay? And that actually implicitly captures some longer-term effects, or it doesn't have to be long-term. It could be still local, but with richer observations, such as a high-dimensional real vectors and so forth. And then, what you further want to exploit is that these transformations, even though written in the explicit way, very often you do not need to explicitly model it, okay? Because we again go back to our old friend of kernel trick. Your needs to manipulate them is always in the form of a product between a pair of features. Okay, therefore, this is a matrix, and every element in that matrix is a dot product of some, transformed feature vectors, which may come from a space of, higher dimension or infinite dimension, but you need to only handle the outer product of it, right? So that naturally allows you the kernel trick. You can always directly, model, this type of matrix using a kernel function, and that gives you, almost the arbitrary power of modeling continuous random variables, as long as you can come up with legitimate kernels to really capture their dot product properties. Okay, so that's actually a very important feature. Your kernel allows you to really, transform, a real feature vector, into some infinite kind of, feature vectors in a Hilbert reproducing kernel Hilbert space that satisfies all the, vector properties, for, dot product, summation, and transformation, all that, without explicitly requiring you this transformation. So that's a literature I'm not going to have time to cover. It was covered in our earlier version of the graphic model lectures a few years back, which is called the kernel graphic models. Okay, so over there, the design of the conditional probability matrix becomes the design of a kernel matrix for manipulating features and feature interactions. Okay, now I'm going to wrap up. Again, just to revisit, there is this, nice complementary properties of a traditional EM-based latent variable model approach versus the newer, recent Spectral technique-based graphic models, Spectral graphic models without latent variables. And you can see that here you are not really trying to learn the same model as you prescribed in the latent space graphic models. For example, you don't want to learn the transitional matrix or probability of the latent states in HMM because you're not going to use it for prediction. They are not the goal of the learning. They are the intermediate steps to calculate a predictive outcome. So the spectral algorithm allows you to bypass that. And as a result of bypassing the latent variable learning, you are going to have a local minimum free algorithm, and it is trivially consistent, and it is very fast. Right. So the only, of course, major hurdle for this model being used is how to derive models. There is no automatic and standard way of deriving them. You have to study every model one by one. There are modern work by Anima and by a few others, applying the spectral technique to even fancier models like topic models, like mixed membership models. And in theory, every model, if you work hard enough and look into the actual formulation, you could replace them with a spectrum formulation that is either equivalent or approximating the original effect. Yeah, but it's a manual work. Okay, it really requires some non-trivial algebraic skill, to make that happen. And then there are some technical issues in here in EM. You have the advantage of not needing to deal with negative numbers in probability. So there are no bugs basically in the algorithm. And here there are sometimes uncontrollable bugs which cause your matrix to be uninvertible and so forth. That's usually because of the way you rotate the matrix is not quite comfortable. Then it causes some, while you are projecting out the latent variable, you may be introducing some, other algebraic artifacts. So you have to, surgically handle that by introducing more rotational matrix to change the orientation. But other than that, there are benefits such as incorporating long-term, long-range effects to get feature-based, graphic models, and also to have a Hilbert space embedding, for nonlinear effects and infinite-dimensional expansion and so forth. So I think this is a very interesting and intellectually intriguing technique that could, bring you a nice outcome. I would say in the past several years, several of the state-of-the-art results, in NLP, maybe also in computer vision, was produced by spectral algorithm. That was before the wave of deep learning. Okay, even the classical Knisonet language model, for example, for language modeling, was also in fact beaten by a spectrum approach. That was actually a 20-year world record beaten, by a new method. It was pretty substantial. So I think it has a lot of potential. But now, of course, attentions are not as high because you have a more powerful technique in deep learning, which of course are driven by big data. You actually could, in many cases, achieve even better results if you are able to train good models using those data. But I think there are problems where data are not so rich, and structures may be also more subtle. Then this technique could still give you some advantage. So with that, I'm going to close today. Next week, I'm not in town, so my student will continue with 2 more lectures. One is on the Gaussian graphical, the Gaussian process that gives you another way of doing non-parametric Bayesian inference. And then I have another lecture on distributed machine learning, how to get the model more scalable in size and also in dimension. Okay, and then I'm coming back to close the whole lecture for the semester. How are you doing on the class project? You have another, say, 2 weeks to wrap up, right? So I highly encourage you to plan your time accordingly to hopefully have some fun results. And NIPS deadline is very close. Hopefully, some of the papers can be. In fact, in the past, it was almost like a ritual that people have feedbacks from the class presentation. And it's like almost like a free review basically for your NIPS paper, and then you modify it. A couple of good NIPS papers were produced in this way from this class. Okay, so I hope you good luck. All right, thanks. Bye.